Hello detectives of data, welcome to AlgoStock, where we unravel the mysteries of algorithms, one clue at a time. Today, we'll explore an exciting tool from the world of machine learning, XGBoost Regressor. Specifically, we'll dive into how it can predict stock prices using quantile regression and why this approach is often more insightful than traditional methods. If you've ever wondered how traders predict price ranges or manage risks, this is the video for you. Let's start by getting familiar with the basics. Oh, and by the way, if you're unfamiliar with how XGBoost works conceptually, don't worry. I've already made a detailed video explaining the entire working of XGBoost step by step. So, feel free to check it out for a complete foundation. For now, let's focus on the math. Let's start with something most of us have already seen, mean squared error, or MSE. XGBoost typically uses this loss function when you're building a standard regression model. It predicts the mean of the target variable. In simple terms, this measures how far our predictions y-hat are from the actual values, y, and our goal is to minimize this value. But how does XGBoost decide where to split the data? When building trees, that's where the similarity score comes into play. XGBoost works by taking gradients and Hessians, basically the first and second derivatives of the loss function. Let's calculate these for MSE. This tells us the direction to update the prediction to reduce the error, and this captures the curvature of the loss function. Now, for any node in the decision tree, XGBoost uses the gradients and Hessians to calculate a similarity score, which measures how good a particular split is, where G is the sum of gradients for the data points in the node, H is the sum of Hessians, and lambda is the regularization term that controls overfitting. Next, XGBoost evaluates the gain from splitting a node into two child nodes, say L and R. If the gain is positive, XGBoost decides to split the node because it reduces the loss. Let's analyze a trend to see the working of XGBoost when it uses MSE as the loss function. Suppose we want to analyze this trend. After applying XGBoost Regressor with default loss function of MSE, we get this red line as the prediction line. Now, MSE penalizes large errors quadratically. This means that if there are a few data points with very large deviations outliers, they dominate the MSE, skewing the evaluation. MSE focuses on minimizing the average squared error, which centers predictions around the mean of the target distribution. This is not always desirable, especially in financial or trend analysis, where understanding the range or uncertainty is more valuable than just the central trend. Now let's move on to something a bit more advanced, quantile regression. This is incredibly useful when you need prediction intervals instead of just a single point estimate. For example, in stock price prediction, traders might need a range, an upper limit, a lower limit, and a midpoint. Quantile regression allows us to calculate these intervals. The key here is a new loss function called quantile loss. Unlike MSE, which focuses on the mean, quantile loss predicts specific percentiles of the data distribution. Quantile loss applies asymmetric penalties for predictions that are above or below the actual values. In the cases where prediction is above the actual value or overestimations, the penalty is 1 minus q multiplied by predicted value minus the actual value. The higher the quantile value q, the smaller the penalty for overestimations because the focus is on ensuring that predictions are rarely below the 95th percentile, and in the other cases of underestimations, the higher the quantile q, the larger the penalty. We will explore how XGBoost uses these concepts shortly for predictions. Now, let's derive the gradients for quantile loss. This part is crucial for understanding how XGBoost handles splits with quantiles. In order to calculate gradient, we take first derivative of the loss function. In the cases where actual value is more than the predicted value, gradient becomes minus q. And in other case, value of gradient becomes 1 minus q. Since quantile loss isn't smooth, XGBoost approximates the second derivative. A common approximation is to use as Hessian equals 1, essentially treating the Hessian as a constant. So, that's the only difference in the usage of quantile loss function and MSE. Both loss functions use the same similarity score and gain formulas to grow the decision trees. Alright, let's start with the base prediction, which is the very first guess your model makes before any trees come into play. For MSE, this base prediction is the mean of the target values. Why? Because the mean minimizes squared differences. It's like saying, on average, where do we expect to land? For quantile loss, the story changes. The base prediction here depends on the quantile. For q equals 0.5, it's the median because the median minimizes the sum of absolute errors. Next up, the gradient. This tells us how wrong our predictions are and which direction we need to move to fix them. For MSE, it's straightforward. This is just the difference between the prediction and the true value, scaled by 2. But for quantile loss, things are a bit more nuanced. The gradient depends on whether we're overestimating or underestimating. If we're underestimating, then the gradient is q, and if we're overestimating, then the gradient becomes q minus 1. Now, let's talk about the Hessian, which is the second derivative of the loss function. It measures how fast the gradient is changing. For MSE, it's a constant value, because the loss curve is a simple parabola. But for quantile loss, the Hessian is always 0. Why? Because quantile loss doesn't involve any curvature, it's piecewise linear, so no second derivative is needed. Moving on to the similarity score, this is what decides how well a split in the tree separates the data. For MSE, G and HI are the gradients and Hessians, and lambda is a regularization parameter that prevents overfitting. For quantile loss, it's the same idea, but simpler because Hessian equals 0. So, the similarity score depends entirely on the sum of gradients. Now, let's talk about gain. This measures how much better our model becomes after splitting the data at a certain point. MSE considers the improvement from both the left and right child nodes compared to the parent node. For quantile loss, again, no Hessians means it's simple. Here, splits are guided by gradients alone. Next, we calculate the leaf value. This is the correction made by each leaf in the tree. For MSE, again, gradients and Hessians come into play. In the case of quantile loss, the leaf value isn't calculated using gradients or Hessians. Instead, it's determined by the quantile of the target values within that leaf. This approach ensures that the prediction aligns with the chosen quantile, directly minimizing the quantile loss for that group of values. Once we have the leaf values, we can compute the final prediction after one tree. Here, eta is the learning rate, which controls how much we adjust the predictions based on the tree's corrections. Finally, when we've built multiple trees, each tree adds its contribution, gradually improving the predictions. And that's it. These are the formulas that make XGBoost such a powerful tool for regression tasks. Remember, the key difference between MSE and quantile loss lies in the asymmetry of the loss function and how it handles outliers or skewed data. Let's connect this concept back to some practical scenarios in stock trend analysis. When we use the default approach in XGBoost, it predicts the mean of the target variable by minimizing the mean squared error at MSE. Now, here's the thing about the mean. It's great for understanding the central value when your data is symmetrical and free of outliers. But the moment your data has outliers, those extreme values that don't follow the general pattern, the mean can get heavily influenced. For example, imagine most stock prices in a dataset fall between $40 and $60. But there's one extreme value at $8. The mean will shift downward to accommodate that outlier, even though it doesn't represent the actual trend of the majority of the data. This is where the median comes to the rescue. The median isn't affected by outliers because it represents the middle value when the data is sorted. By analyzing the median, we focus on the central tendency of the data while ignoring the noise created by those extreme values. It gives us a much clearer picture of the trend. To understand the price range of a stock with a 95% confidence interval, we can use quantile regression to analyze both the lower and upper bounds. Here's how it works. The 2.5% quantile represents the lower bound. It tells us that 2.5% of the data falls below this value, essentially capturing the lower end of the price range. On the other hand, the 97.5% quantile represents the upper bound, showing the point above which only 2.5% of the data lies. Together, these two quantiles give us the spread of values where we expect the price to fluctuate with 95% confidence. So, detectives, today we uncovered how XGBoost Regressor can be used for quantile regression to analyze stock trends. Whether you're an analyst, a trader, or just a curious learner, this approach can help you uncover hidden patterns in the market. If you found this video helpful, don't forget to like, share, and subscribe to XGBoost. Drop your questions or ideas in the comments below. Until next time, keep solving mysteries with data. Happy learning!